I'm just to introduce myself. I'm Joël Huber. I would have been going to IMO if it wasn't online because of Corona, and I was at an International Olympiad of Informatics last year and probably hope to qualify this year again. So we're going to look at some, I said it like a weird functional equation, but actually it isn't a functional equation, it's more of a problem about sequence, I think. About some strange property, but we'll see, I guess. So let's look at the problem. It's from IMO 1988, and a function f from the natural. So the natural is defined by, I'll just let you read through it. Are you done? So I changed the value from 1988 to 2020 for reasons of actuality. And so first thing we could maybe look at is we can note that these equations uniquely define the problem. We can look at, if we want to calculate some value, we look at the residue modulo 4. If the residue is, what it's congruent to modulo 4. If it's congruent to 0 or 2, then we just use the first one, f of 2 and f of n. And if it's congruent to 1, we use the second one. And if congruent to 3, we use the third one. So for example, to calculate f9, we've used the second one to get that f of 9 is actually 2 times f of 5 minus f of 2. And we will need to find the number of fixed points, that is the number of values such that f of n equals n. So this problem, it's a bit, I don't know, it's not easy to see where to start. So the best thing to do is probably to write down some small values. And you don't have to calculate them by yourself. I did this for you. And so I calculated a list of small values, which you can calculate, and which you probably calculate at an IMO exam in a very short time. And so I think since since the problem is asking about fixed points of the function, I thought it would be nice to maybe mark them. And now I want to ask, does someone see something interesting? Someone?
Well, up to now, you have lots of them, right? All odd, right? So
yes, it seems like the values are the odd numbers. So, I mean, it would be nice to, we could now start trying to prove, but I think there's a small problem. We wouldn't get that far because f of 11 is actually equals to 13. So this theory is actually out of the window. So maybe we can have the idea to calculate some more values, but I think it kind of gets chaotic, and I don't know, maybe just look at it and tell me if you see some pattern. I don't really see a pattern if I look at this thing here. And I mean, the fixed points are also like distributed in a random manner. I mean, we can see that only odd numbers can be fixed points, but
maybe all prime numbers are fixed points, but not all fixed points are prime numbers. Except 2.
9 is not.
No. You can look at f of 13 and f of 15.
Yeah.
So this somehow destroys the correlation between primes and function. So maybe I also prepared some other graphic, and I still don't see any nice thing. So we will probably need to look at the problem from another way. I think we need to change perspective. So how can we actually change perspective? And I just want to ask this question again, if someone has an idea of how we could possibly change perspective. I'll just let you think for a minute. I can just give you the values again. So
Oh, we're not that bright.
So maybe let's just continue. Did anyone have an idea of how we could possibly change perspective? Did anyone have an idea?
Personally, I'm stuck with trying to find a pattern that I can't see, so no.
The thing is, the pattern is like, it's not really, I think it's not really possible. I mean, it's possible to see the pattern like this, but I mean, no human would see the pattern looking at it like this. So the solution, like the perspective we need to look from the perspective we need to take is we need to look at it from binary representation. And why binary representation? There are actually several clues in the problem that say that it's maybe a good idea to choose binary representation. An example is that like stuff like 2n, 4n, and so on are like not that hard to handle. Like 4n is actually moving the binary representation 2 steps to the left, and we can then +1 is only like adding a 1 in the end and something like this. And then we also get with f of 2n equals f of n, we see that f of 2k is equal to 1. So this is maybe, if you look at the values back, we can see that f of 1, f of 4, f of 8, f of 16, f of 32 are all like equal to 1. So this may be another hint. And then for me, I think base 10 feels unnatural sometimes. And the last clue is probably something you wouldn't do at an IMO exam, because if you look at like the first 1,000 values of the function, we clearly see that this is somehow related to powers of 2. So we now actually found another perspective to look at, but this doesn't mean we know what the function is actually doing. So I wrote the values for you in binary representation, and I'll just let you look at them again if you maybe find a pattern. If someone sees something interesting, just tell, otherwise I
So
continue.
it's metric, or what, like when you can kind of read it from left to right or from right to left?
Sorry?
So it's those two numbers, you read them from left to right or from right to left, and that's the same?
Yeah,
you read them from right to left, actually. I wrote them like in the oh no, I mean like the smallest, the smallest power of 2 is on the right.
Yeah, but the function is like if you take a number and read it the other way around, right? That's the function. That's it.
It just reverses the binary representation of the number. And if we go back to the values we had before, I mean, how to see this pattern, like just looking at these values. I mean, this was an IMO problem 3, so the hardest one, and I don't think this is for no reason, because I mean, if you don't have the idea of looking at the binary representation, you're completely lost. There's nothing you can do. And if you then have the idea to look at the binary representation, then it's not that hard to spot anymore. Just looking at these values, you can see that like each of the values we get is just the input reversed. So this is the hard part. So let's now the hard part is figuring this out. Now the a bit easier and more technical part is like prove this observation. And to start to prove this, we remember that I said in the beginning that the given equations uniquely define f. By looking modulo 4, we can do this by induction. And then we define the function that reverses the binary representation as g. And if g satisfies the same equations, then because these equations define the function uniquely, it must follow that f is equal to g. So we just need to prove these equations, and the first two are kind of obvious. I don't look at them had looked at them closer. So let's go to g of 2n equals g of n, and let's write n in binary. I had some difficulties doing indexing like the number, so I just decided to do a to set a c instead of like a1, a2, and so on. And so gn is just the binary representation reversed. And now we can see that 2n is actually just placing a 0 at the end of the binary representation at the the new least important bit. And then if we change if we flip the direction, then the 0 is put in front of the number, and a 0 like in front of a number in a binary representation doesn't change anything. So we get that g of 2n is actually g of n. The second equation is kind of a bit more difficult. To do this, we introduce again n and 4n plus 1 in binary. And we can see that 4n plus 1 is like n written in binary, just append a 0, 1. And then if we change it, then we get like 1, 0 backwards, the number n backwards. And this is actually like g of n plus this 1 in front is some power of 2. And for the moment, let's just say it's like 2 to the k. We can find an explicit formula for k, but we will see that this is not needed for the proof. Because if we look at g of 2n plus 1, we can see that like we also get g of n and a 1 in front, but this one is just like one place to the right from the one before. So we can write it as 2 to the k minus 1. And then because we have 2 g of 2n plus 1 in the equation we want to show, we may just like duplicate the thing we had. And so we get to 2g of 2n plus 1 is equal to g of 4n plus 1 plus gn, and rearranging the stuff, we actually get what we want to prove. And then we have the other equation. I leave this out because of time and because it's not that interesting in my opinion. It's like kind of the same thing again, just change some values and use 3 instead of 2. And so we have proven that the function is actually the function that reverses the binary representation. So in the end, to solve the problem, we need to get back to the fixed points. And actually, fixed points are nothing else than binary palindromes. So we only need to count like binary palindromes between 1 and 2020. With some counting stuff, we can find out that there are like 94 binary palindromes from 1 to 2048, which is kind of close to 2020. And there is one number like 2047 is equal to like 11111 and so on in binary representation. It's too big. And when we write 2020 in binary, we can see that this is like the only number that is too big, since 2020 already starts with a lot of ones in binary representation. And so we have 93 fixed points in total, which solves the problem. Thank you for listening, and I hope you enjoyed the problem.
Well, thanks a lot.
Thank you.